Hello, this is me practicing for my talk at ATTI in a few days. I'm going to be talking about topologies on semigroups. So the idea is I'll just give the talk with no prep and see how well it goes and see how close it is to the right amount of time. This is supposed to take 40 minutes in theory. How do I make this fit this screen? Um, I guess it's also a test of technical things. I don't know if I've given a talk on this Mac before. Uh, that's not right. Is there a full screen button? Maybe F? Alright, this isn't the problem I was expecting. Full screen. Okay, that looks right for me now. I don't know if it's recording correctly though. So, yeah, so if I do this, and then I do that, and then if I do single page, that's a single thing. Let's make it look like this. Um, does it actually pay attention to what's on my screen as opposed to what's in the window? That's weird. Okay. Is it that vertical? Oh, I don't like this software at all. Alright, how awful is this? Yeah, I think that's good enough. You can read it. Alright, and I can click through it. So let's get on with the talk, and I'll time myself on my watch. And hopefully it'll take around 40 minutes. I want a stopwatch. Okay, so today I'm going to be talking about reconstructing topologies on monoids. Um, the talk is by me, Luna Elliott. I currently work at the University of Manchester. The talk will be, in some sense, a sort of survey of a bunch of results in this area. A lot of the results are with me and collaborators, but this is not like focused on the results of one particular paper. So, I'll be talking about lots of things which I wasn't involved in, but among the ones I was involved in, these are the people who co-authored with me at least once on those things. So this is Serhi, Julius, Zach, James, Michał, Jan, and Michael. Um, yeah, okay. So reconstructing topologies on monoids. So first, what's a monoid? Well, a semigroup is. People probably know this already, but perhaps people are less familiar with inverse semigroups. So a semigroup is just a set with an associative binary operation. A monoid is a semigroup with an identity. Every semigroup can have an identity adjoined to it. So for the most part, monoids and semigroups are sort of interchangeable as concepts. So you shouldn't be too sort of preoccupied with which one I'm saying, and I might sort of switch between the two arbitrarily. An inverse semigroup, if you're not familiar with semigroup theory, then an inverse semigroup sounds a lot like a group. It's a semigroup with inverses, but the inverses are a weaker sense of inverse than groups. So all groups are inverse semigroups, but not all inverse semigroups are groups. So the semigroup inverse has to satisfy these properties. Inverse semigroups form a variety of algebras. They satisfy certain laws, and they're defined by these laws. So this law, the first one is basically saying it's a local inverse. S inverse undoes S, but only in the presence of S. Yeah, inverse of inverse is the original thing, and this is the thing about idempotence commuting. So the idea is that SS inverse and TT inverse for various S and T in our semigroup are thought of as like local identities. And these identities commute with each other. So you think of the idempotents in this of an inverse semigroup as sort of partial identity functions, and this is the vibe that will go. An inverse monoid is just a monoid with inverses. So it's an inverse semigroup which has an identity. So semigroups and monoids are basically the same thing for my purposes. Okay, so how the way they think about them is, at least the way I'm going to think about them, is using Cayley's theorem and Wagner-Preston's theorem, which is basically the same thing. So Cayley's theorem, as I'm sure you all know from group theory, says that if you have any group, it's a group of permutations of a set with composition of functions, and this generalizes to monoids. Every monoid is a set of transformations of a set together with compositions of functions. And the Wagner-Preston theorem is just that for inverse monoids. So the way you think of an inverse monoid is it's the set of partial bijections of a set together with composition of partial functions. And the inverse of a partial bijection is, of course, just you invert the partial bijection. The Wagner-Preston theorem is significantly harder to prove than Cayley's theorem, but it is very sort of like, I think this is sort of a good way of thinking about inverse semigroups if you're not used to them. So you just think of them as one of these types of inverse monoids, and it turns out that this characterizes all inverse monoids. All right, so the way that I'm going to think about this in practice is monoids, you want to think about endomorphism monoids, so structure preserving maps of things. Inverse monoids, you want to think of partial automorphisms of things, so isomorphisms between substructures of a thing. And groups, you think of automorphism of groups of things. This is the way in practice I'll think about them. So you can think about them in the abstract in the way I described before, but this is the way that I'm actually going to think about them in this talk. Particularly with inverse monoids, I think this is easier to understand than the abstract definition. Okay. So I'm going to talk about topology. So topological semigroup, it's in general a topological algebra in the sense of universal algebra. It's just a universal algebra whose operations are continuous with respect to some topology on the underlying set. And this is no exception. So a semigroup, you just got a semigroup. You have a topological semigroup, you have a semigroup, and you have a topology on the underlying set of your semigroup, and the operations are continuous. In this case, there's only one operation, which is multiplication, and it has to be jointly continuous, at least in the standard notion of topological semigroup. There are weakenings of this which are also interesting. And topological inverse semigroup is the same, except you've got also an inverse operation, which maps the thing to its inverse, and that is assumed to be continuous as well. In particular, topological groups are equivalent to looking at topological inverse semigroups, which are groups. Topological groups are usually assumed to have continuous inverses. I think a topological semigroup that's a group is usually called a paratopological group. Okay. So important examples, I'm sure you already know almost all of these. So the reals with various operations are continuous, and it's a semigroup with various operations. I think the reals with max is an interesting example. Like it just takes two real numbers and outputs the bigger one. This is a semigroup operation. It's very different from the sort of more common operations like multiplication, but it's a semigroup operation and it's continuous because the sort of max is the topology and the reals is compatible with the order in a nice sense. And the matrices also form a topological semigroup, and they're like a topological ring even. And you can replace reals with your favorite field, which has a topology on it, including the complex numbers. So profinite groups are topological groups. So profinite semigroups, if you're familiar with those. If you have a compact metric space, you can look at the continuous maps from the space to itself. And this is a topological semigroup with respect to the compact open topology. And if you look at the invertible ones, you get a topological group. Discrete semigroups are topological semigroups. They're just sort of trivially. So in some sense, which is sort of cheating, all of semigroup theory is topological semigroup theory, where you're just sort of focusing on the discrete case. Although that's perhaps a bit cheating, but this is true in some sense. Okay, so the question I want to talk about in this talk is, if I have a monoid, then what topology should I put on it? So the premise is monoids are interesting, and there have been examples in the past of people using topology to do stuff with various monoids. So if I have a monoid I care about, can I put a nice topology on it to sort of study the monoid better? And this also gives me an excuse to use lots of topological facts because I'm a topologist and I like topology. Okay, now when you look at it first, this is like you look at it from the from a certain perspective, this is like a very hard question because you're asking which topology, which element of the power set of our monoid is the best one. So a topology is a set of is a family of subsets of a set. So it's an element of the power set, and this is like really big. So like there's lots of topologies on a given set, assuming the set's reasonably big. So this is, it sounds like, if you haven't thought about it much, this is like a very hard sounding question, and it is quite a hard question in the general case, but you can sort of pick a best one in many natural cases. Okay, so first I need to sort of exclude certain trivial things. So as I mentioned before, the discrete topology on any semigroup is a semigroup topology. The operations are continuous because like everything is continuous when you use a discrete topology. And by similar reasons, the indiscrete topology, where only the empty and universal sets are open, has the same property. So you want to sort of exclude these sort of boring cases which don't tell you much. So you want to, the standard way, I missed the letter C in the word compact there. Sort of the standard way is to assume your topology has certain nice topological properties. And I think that sort of the most common topological property to assume is Hausdorffness. A lot of people dislike working with non-Hausdorff topologies, and certainly that's a useful property to have. It's also a hereditary property, which is good. A very nice thing, which is true about topological semigroups and topological algebras in general, is that if I take any sub-semigroup of a topological semigroup and give it the subspace topology, it's automatically a topological semigroup. And it's nice when our topological structure is compatible with this. A second countable is also a nice property, which I like a lot because it's also hereditary, and it's sort of, in the same way Hausdorffness requires you to have a certain amount of open sets, second countableness requires you to sort of not have too many. And if you want to be slightly more presumptuous about your space, things which I tend to like to look at are Polish semigroups. It turns out that a very large proportion of the semigroup topologies I'm interested in tend to be Polish. So this is a second countable and completely metrizable. And this gives you access to the bare category theorem, which is very good. And also compactness is very good for obvious reasons. This gives you the bare category theorem, and it gives you a whole bunch of other crazy stuff. Although in practice, a lot of the semigroups I'm interested just don't have any interest in compact topologies, which is why sometimes I usually am content with Polishness. And honestly, I'm even content with much weaker than Polishness. It just happens that Polishness comes up a lot. All right. So, which semigroups do I care about? Well, I care about all semigroups, but there's sort of a natural starting point, in my opinion. So a lot of this talk is just going to be exposition about things which already are known. I don't think there's any proofs in this talk. So, but yeah, I think these are interesting results that people should know about. Okay, so I mentioned before from Cayley's theorem that every monoid embeds in a transformation monoid. Every monoid can be thought of as a monoid of transformations on a set. So sort of the first, a reasonable starting point for monoids to topologize is the full transformation monoid on a set. And I'm looking at a countably infinite set, which may as well be the natural numbers. I'm also interested in larger sets, but in practice, most things that you're interested in for this full transformation monoid on infinite sets is sort of the same for any cardinality of set. So I'm going to focus on the countable ones for now. Is the countable underlying, like a countable set that I'm acting on by transformation. So I'm looking at all the maps from the naturals to itself as a thing. So there's a theorem by me, Julius, Zach, James, Michał, and Jan, which says that there is a unique second countable Hausdorff semigroup topology on this semigroup. So at this time, we actually have a very sort of strong answer. This is the best topology in the sense that it's the only topology which has these fairly mild assumptions. And this is sort of advertisement that this is not an untractable question. We have an answer which I think is quite definitive in this quite important case. And the topology is what's called the pointwise topology. I'm going to be talking about the topology a lot, particularly a lot of submonoids of this monoid are important, and we can consider, as mentioned before, the subspace topology induced on those submonoids. So this topology will be very important throughout the talk. And this is this is the pointwise topology. So the topology is the topology of pointwise convergence, where we consider the natural numbers to be discrete, and it has a subbasis consisting of these sets. I like to put my functions on the right of their input, but that's not that important. So this is just like you have a subbasis. Like your topology has the power to force a function to map a particular point to another particular point, and that's how the topology is defined. It's a nice space. This is the Baire space. It's a Polish space, and it's zero dimensional, and it's a very nice space. It's not a compact space though. Okay, so endomorphisms of relational structures. So I mentioned a second ago, I'm going to look at submonoids of this monoid. So there's a famous folklore theorem which classifies which submonoids of n to the n are the endomorphism monoids of relational structures, which is a very natural class of monoids to look at, endomorphism monoids of things. So a submonoid of an n to the n is the endomorphism monoid of a relational structure precisely if it is closed. And by closed, I mean it's closed in the topology I just described. So this is somehow even more advertisement that the last topology is the sort of the best one. And there is other model theory stuff you can do. There's a theorem of Budersky and Juncker, which says that if I have two non-contractible omega categorical structures, then their endomorphism monoids are topologically isomorphic. So there's an isomorphism between them which preserves the pointwise topology, if and only if they are they're positively existentially bi-interpretable. So this gives you a very strong connection between the model theory of the structures and the topological algebra of the endomorphism monoids of the structures. It's very good. Non-contractible means that it does not have a constant endomorphism. Unfortunately, this is quite a strong hypothesis, but there are certainly many things which satisfy this. I think I'm talking too fast. So I think the paper contains statements of the form that you can't do this. You can't deduce contractibility using the topological isomorphism type of the endomorphism monoid. So this is it's like you might want to sort of remove this assumption, but there's evidence that this assumption can't be removed, at least not in a natural way. But even as it is, I think this is a very important result, and it sort of again gives you the idea that the topological algebra is keeping the important information. It describes it quite nicely. Okay, so it's another reason that this is sort of the best topology. So submonoids, there's lots of things about submonoids. I just mentioned one. So there's a theorem which says, there's a theorem which classifies when a thing embeds into n to the n, and not just as a closed submonoid, but as any submonoid. So, sorry. So if you have a Hausdorff semigroup, then it embeds into n to the n, if and only if it has a subbasis consisting of the classes of a countable family of right congruences. I should say countable index right congruences. That's an important part of the hypothesis. So the submonoids of the topological semigroups which embed into n to the n are precisely those which are based using right congruence classes, and only countably many of those. This is slightly misstated. Which sort of makes sense if you're a semigroup theorist, like asking where a point goes in the action of n to the n defines a right congruences, and this is sort of how that works. So this tells you that the algebraic structure needs to be sort of compatible with the topology in this way, which works for n to the n, and this exactly describes how embeddability works. And this is also sort of a generalization of a well-known group theory version of this result, which I'll talk about in a minute. And there's a sort of more recent result by Bordilla, Mitchell, and Perez, which says that if you assume your semigroup's compact, then we actually have like a very strong connection between topology and algebra, which says that embedding as a topological semigroup into n to the n is the same as embedding as a topological space. So the algebraic structure actually doesn't serve as an obstacle at all. It's entirely the topological structure. In particular, the subspaces of n to the n as a space are very well understood. So a compact semigroup embeds into n to the n precisely if it's a metrizable and totally disconnected semigroup, which is Pretty cool. Okay, so symmetric inverse monoid. So I mentioned before that semigroups sort of correspond to transformation semigroups, which are like the endomorphism monoids of things in some sense. And inverse semigroups are the partial isomorphism monoids of things. And the symmetric inverse monoid is the analog of the full transformation monoid. So the symmetric inverse monoid IN is the inverse monoid of all partial bijections of the natural numbers. And again, we have a similar result to the one before. So there is a unique second countable Hausdorff inverse semigroup topology on IN. And this is very similar to the pointwise topology. So again, we can insist that a function maps a certain point to a certain point. But now, because these are partial functions, I can also demand that a certain point is not on the domain of my function. And to be compatible with inversion, I can also assert that a certain point is not in the image of my function. So this is very nice. And it turns out this topology is homeomorphic to the previous one, and it's Polish and it's not compact. A lot of people like to consider the symmetric inverse monoid with a different topology, which is a compact topology, but that topology does not have jointly continuous multiplication. So it's not a topological inverse semigroup with that topology, but it does have a lot of nice properties. So it should be noticed that there are arguments that can be made that this isn't the best topology for IN, but yeah, it is the only second countable Hausdorff inverse semigroup topology. So I think that's a pretty good argument that this is potentially the best topology, but I guess it depends on your framework. Maybe you care about compactness more than joint continuity. I like joint continuity, so this is my favorite one on IN. Okay, and a lot of this stuff from before works. Although in my experience, model theorists tend to put less focus on inverse monoids than monoids, which I think is quite contrast with the semigroup community. Like the semigroup community seems to care a lot about inverse monoids. So I think it sort of surprises me that model theorists are less into inverse monoids. There seems to be a sort of gap in the literature. I don't know why this is. This is a theorem. This is a more recent theorem by Hampenberry Christensen. This is, I believe, Jan's student. So an inverse monoid of IN is the partial isomorphism monoid of a relational structure. So this is corresponding to the endomorphism monoid of a relational structure, precisely if it's closed and it contains all the partial identity maps. So before we just had isomorphism, now we have this extra condition. So you can have a closed submonoid of IN which doesn't have the partial identity maps in it. But obviously, if you're the partial isomorphism monoid of a structure, you have to contain the partial identities, because like a partial identity function is clearly a partial isomorphism. So this is an obvious condition you need, and it turns out this is the only extra one you need. And before I said there's this correspondence between topological isomorphisms between endomorphism monoids and this certain type of interpretability. And there's just no result like this in the literature for partial isomorphism monoids, and I don't know why this is. So I think somebody should prove a theorem to this effect. They just haven't done it yet. So you can ask, so conjectured, open-ended theorem-y thing. So if two structures are nice in some way, then their partial isomorphisms are topologically isomorphic if and only if something about interpretability. I feel like something like this should be true and this should be in the literature, but it currently isn't. So that's a thing for the audience to figure out. Okay, and then to embeddability of things. There's this. Before there was a thing about right congruences. We do have a result for symmetric inverse monoid using congruences. It's much more technical though. So the theorem says that if I have a Hausdorff inverse semigroup, it topologically embeds an IN if and only if it has a subbasis consisting of the classes and inverses of the classes of a countable family of Wagner-Preston congruences. And this is not as satisfying because it has hidden in the theorem like this notion of Wagner-Preston congruences, which we made up for the purposes of the theorem. But it's like not totally unreasonable, and it's in the same sort of spirit as the previous result. Also, I think I just spelled Wagner inconsistently over some slides. I did. Okay. I think it is spelled multiple ways in the literature, but I should probably be consistent. Yeah. Okay, and similar to before, embedding is entirely, if you assume your thing is compact, then embedding is entirely a topological thing, which is very cool. So um, if you have a compact inverse semigroup, then it embeds into IN as an inverse semigroup, if and only if it embeds into IN as a space. And as I mentioned before, IN is the same space as n to the n. So this is the same as being metrizable and totally disconnected. So this is a lot of almost everything just works nicely for IN the same way it works for n to the n. So it's a very nice object. And obviously I can't forget group theory. Okay, so there's this theorem of Kekrich and Rosendahl. This is older, although it's not actually that old. It's like 2007 or something. It says that there's a unique second cannibal Hausdorff group topology on the symmetric group. In fact, I think they even prove that the only separable group topologies are the the usual one and like the trivial discrete one. So this is a very powerful result. And it's the topology induced by this the pointwise topology as a subspace. And again, this is Polish and it's not compact. Again, it's homeomorphic to the full transformation line. And this is sort of the canonical thing on the symmetric group. Okay. And there's similar results to before. There's a folklore result which says, similarly to before with endomorphismoids, a subgroup is the automorphism group of a relational structure precisely if it's closed. So it works the same way as the previous two results. And there's a result which says that if you have two non-trivial omega categorical structures, then the automorphism groups are topologically isomorphic if and only if the structures are bi-interpretable. This is sort of even cleaner than the previous results about endomorphismoids. And there's essentially no assumptions on the structures other than being omega categorical. So this is a very powerful correspondence between the topological algebra and the model theoretic structure of the object. Okay, and similar to before, there's a characterization of when things embed even when they're not closed. So how to store topological groups embedded in the symmetric group if and only if the identity has a countable neighborhood basis of open subgroups. This property is called being non-Archimedean. So this corresponds to the right congruence thing, because right congruence is on a semigroup. Right congruence is in a group corresponding exactly to subgroups. And as is often the case in group theory, you can describe everything using like the identity by just sort of moving it around. But this really is the analog of the two results mentioned before. It's just a bit tidier because group theory is a bit tidier than semigroup theory. By Becker and Kekrich. Okay, so there's a bunch of more results in the literature which give you sort of best topologies on things. This is the partial transformation monoid. It has a unique Polish topology. It sort of works the same way the symmetric inverse monoid one does. The monoid of continuous functions on the Hilbert cube. This has a unique Polish topology. It's the compact open topology. This is the monoid of continuous functions on the counter set. So when I say on, I mean from the counter set to itself. So the monoid of continuous function of the counter set, its unique Polish topology is again the compact open topology. And another paper with me, Julius, James, Jan, and Michael. The endomorphism monoids are the following structures, and we have some like conditions, technical conditions. But here are the sort of main examples in my head. The endomorphism monoids of the following structures have a unique Polish topology. In this case, it's always the pointwise one. So the random graph, the random digraph, the random poset, and this is the disjoint union of countably many finite cliques of the same size. These are homogeneous graphs. It even works when n equals 0, although that's a not very interesting example. So this works for lots of things. So sort of how does this work is a question, and so I'm going to get onto standard techniques. So that this sort of two stages in proving that your topology is best. You want to prove it's the smallest good one, and you want to prove it's the biggest group one. That's the biggest good one. So when you try and prove something is the smallest good one, this is typically easier, at least for semigroups, than proving something is the biggest one. Because you just want to sort of force certain things to be open, and then you can use sort of the algebra to do that. This is one of the areas where, perhaps surprisingly, you get more out of the semigroup structure typically than group structure. Because the semigroup structure gives you sort of some non-bijective maps which have to be continuous, which gives you quite a lot of You can deduce quite a lot from this often. Okay, so the lower bounds is sort of easier, and there's lots more stuff in the literature on lower bounds. We're going to talk about lower bounds. Okay, so for any semigroup, there's various natural ways of just defining a topology you put on it. When I say, and I'm not saying a semigroup topology, I'm saying a topology. Sometimes it's a semigroup topology. So these are the first ones are the Frechet-Markov and Hausdorff-Markov topologies. So if you're interested in, for example, a Hausdorff semigroup topology, and you want sort of the smallest one, then sort of obviously, the smallest thing that could work is the intersection of all the things that work. Because like the intersection of topologies is a topology, and like it's going to be smaller than all the ones that work. So you can just intersect all the Hausdorff semigroup topologies on the semigroup, and that's a well-defined topology. And you can ask if it's a semigroup topology, and it often isn't. So the Hausdorff-Markov topology is just the intersection of all the Hausdorff semigroup topologies on the semigroup. The Frechet-Markov topology is the intersection of all the Frechet topologies on a semigroup. The Frechet is another word for T1, if you're familiar with separation conditions. So this is just saying the intersection of all semigroup topologies in which singletons are closed. This term is not used in groups because by standard results for topological groups, if a topological group is T1, it's automatically Hausdorff. But for semigroups, these are actually distinct notions. Okay, so you can just intersect all the stuff you want. The next sort of candidate is you look at the minimum T1 shift continuous topology. So why would I consider that? Like, what am I talking about? So T1, I mentioned before, is famous Frechet. It says that every singleton is a closed set. And shift continuous is a weaker notion for being semigroup topology. It just says that the shifts are continuous. So if I have a fixed element in my semigroup, then I'm claiming that the map, which takes an arbitrary element and multiplies it by that on one side, is a continuous map. Now, why would I say that? Well, because joint continuity doesn't work as well as shift continuity with intersections. So and Hausdorffness doesn't work as well with intersections as T1ness. So if I have some Hausdorff topologies on a set, it's not true that their intersection has to be Hausdorff. And if I have some semigroup topologies on a semigroup, it's not true that their intersection has to be a semigroup topology. However, it is true that the intersection of T1 topologies on a set is T1, and it is true that the intersection of shift continuous topologies on a semigroup is shift continuous. So you can intersect all of those, and you do get a T1 shift continuous topology on your semigroup. So there's always a smallest topology in your semigroup which is compatible with it in this sense. So you can look at that. And there's this Zariski topology, which I think is the most important one. So this is the topology which is defined by the sort of closed subbasis consisting of elementary algebraic sets. So an elementary algebraic set is one like this. It's the set of solutions to, you could call these semigroup polynomials, but these are like sort of maps defined using the semigroup operations. So sort of any algebraically definable set like this is called elementary algebraic. And in sort of nice algebraic structures, these are closed, and you can prove that these are closed in any Hausdorff semigroup topology. And you can just ask, okay, well, what can I deduce from these being closed? So gives you this the Zariski topology is the smallest topology in which these things are closed. And it turns out that the Zariski topology is always a shift continuous T1 topology, but it might not be Hausdorff, and it might not be a semigroup topology, but in practice it is sometimes. So this is sort of a natural place to start because it gives you a concrete family of sets that you know are closed, and hence a concrete family of sets that you know are open. And there's also, if you have an inverse semigroup or a group, you have the inverse Zariski topology, which is the same thing, but you're allowed to use the inverse operations as well. Okay. Okay, so some theorems about these. They're always contained in this way. This is proved in the paper mentioned before. So Hausdorff-Markov is the biggest one, which contains Zariski, which contains minimum T1. And Frechet-Markov is always, obviously contained in Hausdorff-Markov. And this is always T1, so it contains that one. And you can prove that these are all the containments that exist between these four. You only need to consider two semigroups to prove this. So it was proved in this paper that the Frechet-Markov and Hausdorff-Markov topology on IN contain the Zariski, which contain the T1 one. And it was also proved that the Zariski is the same as Hausdorff Markov, which contains the Fechet Markov in the case of the reals with Max. So in reals with Max, this is the order topology, and this is some other thing. In IN, the T11 is the compact thing I mentioned earlier, and this is some weird thing that isn't the semigroup topology. Uh, in this paper, it was not proved that this is actually bigger than the Zariski topology, like strictly finer than the Zariski topology. It was only proved that it contains the Zariski topology. But in a later paper, which is not out yet, but we've written the proof down in a paper with me and Serhi. We know this is strict, so this tells me that in particular this one is allowed to not be contained in this one. And from this result, I know that this one doesn't have to be contained in this one. So this is the best sort of picture for these four topologies. And you can also add like the inverse Zariski topology and stuff to this picture, which is contained in sort of the obvious ways. Okay, so before I go into the next slide, so you usually want to consider the inverse Zariski topology for inverse semigroups and the usual Zariski topology for non-inverse semigroups. So a natural question is, are these different? And the answer is no, even for groups. So it was proved by Goffer and Greenfield, like I want to say 2022-ish, that there's a group where these are different. So these actually are sort of different questions, which is good to know. It was proved more recently in a paper by Serhi, me, James, and Jan that if you take any group which is contained in the infinite symmetric group and contains the sort of finite support symmetric group, then the Zariski and inverse Zariski topologies are distinct. And it was proved even more recently than that if you look in a different setting, look at the homeomorphisms of the interval, and you take any group which contains Thompson's group F, then they're distinct. So there's like loads of groups where these are different, and so these are very different things, and they should be acknowledged as different objects. And certainly they can be different for inverse semigroups. In fact, they're different for the symmetric inverse one. Okay. So more examples of stuff we know about Zariski topologies. So there's another paper by De la Nuez Gonzalez and Gajanezhad, Mariman and Pinsker. I apologize, I've mispronounced the names, which says that if you take the elementary embedding monoids of the following structures, then the Zariski topology is strictly coarser than the pointwise topology. So in these examples, in the examples I mentioned before, so like if I'm looking at the endomorphismoid of a structure, typically the topology I'm trying to construct is the pointwise topology. So this gives us an example where you can construct the Zariski topology, but it's not the pointwise topology, or at least not the usual one. In this case, you get the sort of the metric pointwise topologies for all these Urysohn spaces. And this is strictly smaller than the usual pointwise topology. So you don't always get the pointwise topology, but you do in loads of cases. So there's a theorem of Pinsker and Schindler, which says if I take the elementary embedding monoid of any omega categorical structure with no algebraicity, then you get the pointwise topology. This makes no sense as written. I meant the Zariski topology on the elementary embedding monoid of any omega categorical structure with no algebraicity is the pointwise topology. So it's usually the pointwise topology is the point, but not always. It's sort of because the pointwise topology is supposed to be the best topology in some sense. So you can often construct it as the smallest things just using the Zariski techniques. So some cases where the Zariski topology doesn't work as expected. I already mentioned in the previous slide that it's not always the pointwise topology, but it can sort of fail in more ways. So there's even an omega categorical structure where the Zariski topology on the endomorphism monoid is not the pointwise topology. So remember here I was talking about the elementary embedding monoids, where you're assuming you preserve all first order formulas, not just the relations of the structure. There was also an assumption about no algebraicity. There's a theorem which says that if you take any group with no algebraicity, then the semigroup Zariski topology is irreducible, which is very far away from being Hausdorff. So this says that the intersection of any two non-empty open sets is non-empty, or equivalently, all non-empty open sets are dense. This is very far away from being Hausdorff, and this is like a very large class of groups. And there's a similar thing for homeomorphisms. If you take any homeomorphism group of the Kenner set, which contains Thompson's group V, which is like a countable group, then the group diversity topology is irreducible, and this is sort of gives you a similar vibe to the other result when you're looking at homeomorphism groups. Okay, so more results for groups. So if I take a closed subgroup of the symmetric group with a locally finite algebraic closure and non-trivial center, both very mild conditions, then both the group and its closure in the transformation monoid have a non-Hausdorff semigroup Zariski topology. So this is weaker than being in no algebraicity. And non-trivial center is like a very weak result for the groups we're talking about. Very weak hypothesis for the groups we're talking about. Okay. And when you think of the closure of this, you should sort of the way that you're supposed to think about it, I think, is the elementary embedding monoid of a corresponding structure. So remember, a closed subgroup of the symmetric group is always the automorphism group of a structure, and this corresponds to the elementary embedding monoid of that structure. Okay, and you can also look at the automorphism groups of like certain Frese limits, and this gives you some. It can vary whether or not you get a nice group Zariski topology. Particularly, sometimes it's not a group topology, sometimes it is, and this has been understood for certain examples. So the Frese limit of the finite total orders gives you the rationals. In that case, you have a group topology as your Zariski topology. And if you look at other nice structures, including the Urs and the space and the random graph, you don't get a group topology. So there's a lot of variety in what results you get, depending on the structure. Okay, upper bounds are significantly harder than lower bounds. But there are some results in this way, and a lot of them come from this idea. So if a topological group has ample generics, there's a result by Kekrich and Rosendahl which says it has automatic continuity. In this case, I mean with respect to the class of separable topological groups. So I think the result is slightly more general than this, but let's not go into the overly technical stuff right now. So basically, if I have a group with ample generics, meaning that for every n, the orbit of the group on the n tuples in the group by conjugation, it has for every n, there is a comeagre orbit of n tuples in the action of the group on itself by conjugation. Then it has automatic continuity, which means that every homomorphism from the group to a separable group is continuous. In particular, the group has no larger separable group topologies because you can apply this to the identity map. So that this, under this quite strong assumption, but is satisfied by some important examples, we get a maximal, or even a maximum separable group topology. And you can use this result, you can sort of pull this result up to certain semigroups in certain situations. So this is one of the main tools for this. In particular, this works for the infinite symmetric group. So there's the infinite symmetric group has ample generics. It also works for like the automorphism group of the random graph, for example. Okay, this it's a very strong assumption, which because it requires a strong assumption to get a very strong conclusion. Now, with a much weaker assumption, just any group, we can use this other trick. Although we have to now assume more stuff about our space. So if I have a Polish space, I was assuming the group was Polish for this as well. So if I have a Polish space, and I have another topology on the space which is comparable with it, is a famous result of the Lisson-Solson result, which says that any two comparable Polish topologies in a set have the same standard Borel structure, meaning they have the same measurable sets. And this sort of implies that up to small sets, the topologies agree. So any two comparable Polish topologies on a set have approximately the same open sets. And it turns out if your space is a group, you can remove the word approximately there, and you can sort of move things around a bit, and you can conclude that any two Polish topologies on a group which are compatible with shifting by the group elements are the same. This is very powerful when trying to find maximal nice topologies in a group. And while this might sound not so satisfying if you're interested in semigroups. It actually is quite good because there's techniques for pulling topologies from groups and extending them to semigroups. So the standard trick called property X is quite technical, so I'm not going to go into huge detail. But imagine M is my monoid that I care about, and A is a big subgroup of it. It doesn't have to be a group, but in practice it will usually be a group. So, but A is a subset of the monoid, which I understand well. If I have this technical condition which says that for every point here, I can find an S inside A and two things F and G, which sort of catapult S to this point and map a neighborhood of it onto a neighborhood of this other point. This is called property X. And if you have this condition, which it turns out is satisfied surprisingly often, then you can sort of take any maximality conditions for the topology on A and extend them to maximality conditions for the topology on M. So in particular, if I have a Polish monoid and its group of units is Polish, and then we can conclude that, and the monoid has property X, then you can conclude that the topology on the monoid is a maximal Polish topology, because you can prove that any larger topology induces the same topology on the group by the result mentioned before, and then you can sort of deduce the topology on the entire semigroup from the group part, or at least an upper bound. So property X lets you sort of steal this property for groups, for semigroups. And this works in many examples, and this is sort of the standard technique for proving semigroups have unique Polish topologies using group techniques. And if your group has automatic continuity, as mentioned before using the ample generics trick, you can use property X to sort of steal that for the semigroup. So in particular, because the symmetric group on the naturals has automatic continuity, you can deduce from this that the full transformation monoid of the naturals has automatic continuity because it has property X with respect to the symmetric group. But this doesn't always work. I've mentioned lots of examples where it does work. So I gave, it works for the transformation monoid, the symmetric inverse monoid. It worked for the partial transformations and continuous function monoids of various things, and the endomorphism monoid of the random graph, and a whole bunch of other stuff. It doesn't always work, but sometimes you can sort of fix it a little bit when it does work, when it doesn't work. So there's this result of Pinsker and Schindler, which I was really sort of happy with when this came out, because I tried to figure this out for a while and I couldn't. So it turns out the endomorphism monoid of the rationals, the dense linear order, has a unique Polish topology. But you can't use sort of standard techniques to prove this. It turns out it doesn't have property X with respect to its automorphism group, but it has this thing that Pinsker and Schindler called property X bar, which is quite interesting because unlike many of the previous examples, this group has larger topologies than the pointwise topology, which are like second Kennebel and Hausdorff. They're just not Polish. But you can still use this to prove there's a unique Polish one, which I think is quite interesting. So the endomorphism monoid of Q has sort of the best topology, it's the pointwise topology, but this is like a very non-obvious result. It's much harder than many of the other results I've mentioned. And more recently in a paper with me and Serhi, we did similar things for the integers and the naturals. I was quite happy with these results because, as you probably are aware, the automorphism group of the integers is like tiny. It's countable, and the automorphism group of the naturals is even smaller. It's got one element. So really property X is like totally useless for these two examples, at least if you're considering it with respect to the automorphism group. But it turns out they satisfy this thing called property double X, and it again has a unique maximum Polish topology. So this gives you a nice upper bound, similar to how property X works. Essentially, property double X, it sort of uses... it has sort of property X baked into it, but it also requires you to study the top J class of your semigroup a bit. And the top J class of these two monoids are quite nice, even though they're not groups and they have trivial groups of units. These two don't have a sort of... It's not like the unique Polish topology. In fact, these both have infinitely many Polish semigroup topologies, it turns out. But the smallest one is the pointwise topology, and there's this big one, which is basically the pointwise topology, but you make some stuff near the bottom discrete, because you can get away with that in these cases. And doing this, we prove this more general result, which actually isn't very hard, which says that if you have any totally ordered set, then the endomorphismoid of that thing has the pointwise topology as its Zariski topology. So the pointwise topology is always a lower bound for endomorphismoids of orders. And in some cases, it's the biggest one. In the case of Q, in some cases, it's not, but we could still do some stuff, which I think is quite satisfying. Okay, so here's a question which I think is really fun. Okay, I've been going on for too long, but not ridiculously too long. So counting Polish topologies. So I didn't mention this result before, but if you look at the binary relation moid on the natural numbers, this has exactly 0 Polish semigroup topologies. You can prove that it has automatic continuity with respect to something which isn't Polish, and this sort of breaks certain things. The symmetric difference moid, and this is a paper with me, Serhi, James, and Yan. This is this is a very hard theorem, if I don't say so myself. We classify all the Polish semigroup topologies on the symmetric inverse moid, and there's countably infinitely many of them. They correspond to these things called waning functions, which I think are very interesting. So where am I getting? So there will be a theme to this. If you look at the endomorphism moid of the naturals, but you are looking at the strict order, so in this case the elements of this have to be injective, you can prove that there's exactly continuum many Polish semigroup topologies on that. And if you fiddle with it, there's this other thing. Actually, if you take the right 0 semigroup on an uncountably infinite set of size continuum, then it has exactly 2 to the continuum Polish semigroup topologies. And we have many examples of things which have exactly 1. So we're sort of getting this idea where we can do 0, we can do 1, we can do aleph naught, we can do 2 to the aleph naught, and we can do 2 to the 2 to the aleph naught. And these are sort of all very nice cardinals. So the question is that all you can do? Is there any semigroup which has a different number of Polish topologies than one of those numbers? And I think this is a very cool sort of set theoretic question. And it sort of ties into the idea that from the perspective of Polish spaces, the continuum is the next cardinal after aleph naught, because all uncountable Polish spaces of size continuum. And so some other questions I think are important. So I mentioned this before. Is there anything to do with the sub if you look at the partial isomorphism moids of nice structures, and you can, look at those up to topological isomorphisms, is there any sort of bi-interpretability thing which corresponds to that? There's an open question that was asked a while ago, which is still not answered. Is there any Polish group with a small index property which doesn't have automatic continuity? The small index property says that every countable index subgroup is open. This is equivalent to saying that every homomorphism to the symmetric group is continuous. So I guess I'm asking, is there a semigroup, is there a Polish group with a discontinuous homomorphism to a second countable group, such that all homomorphisms to the symmetric group are continuous? And this is still open, surprisingly to me. Almost certainly the answer is yes, there is one of these groups. That would be my conjecture, but no example is known. And I want to ask, do the endomorphism moids of the integers or the naturals have automatic continuity? Because this was false for the rationals. There are some bigger second countable topologies on that monoid. But we haven't found any for the integers or the naturals. And the way that these results work, I would conjecture that these are the biggest, even second countable topologies, but we don't know. The proofs uses like bare category theory stuff. So yeah, that's the questions, and that's the state of things as far as I'm aware. Thanks for listening. The talk was like 10 minutes too long. I should cut some stuff. Okay. Goodbye.